So my name is James D. Francesco, and I am the Director of Optical Astronomy and the Director of the Dominion Astrophysical Observatory in Victoria, British Columbia. So the Dominion Astrophysical Observatory is part of the Herzberg Astronomy and Astrophysics Research Center, which is itself a research center as part of the larger National Research Council of Canada, which is an agency that promotes the development of science and technology for the benefit of Canadians. So in our research center, we provide access to Canada's domestic and international telescopes by managing that use, providing support to Canada's astronomers to use those telescopes most effectively, by building instruments so that those telescopes can be used at the highest level of technology available, and also recording those data so that they can be distributed and used by the scientists that use those telescopes for their current projects and for projects in the future. I became very interested in space at a young age. I grew up at a time when there was an active moon program. I was born in the late 60s, and so at that time there was a lot of interest and excitement about going to the moon, and that I think pervaded the culture at the time and really laid the groundwork for an excitement about space and an increasing appreciation of the universe. As a kid, I was very interested in all sorts of things about nature. I was a voracious reader and consumed as many books about nature as I could read, and I found it all very exciting. So astronomy was just one of those things. But I think as I was growing up, I just became more interested in the allure of space, and there was just so many tremendous and exciting things that were going on. One thing that was particularly influential in my life was watching a television program called Cosmos, which came out in the late 70s. This program was a PBS program, an American program, that was written and hosted by a man named Carl Sagan, who was an astronomer at Cornell University. And he himself was a great popularizer of science. And this program really unveiled for me the potential that science had in understanding the universe, and how humanity's relationship with the universe was, is, and what it could be. And so I was quite taken by that and found it quite inspiring. And then as I went through high school, I had to start thinking about what I was actually going to do with my life. And I had many other ideas. But one night I was looking up at the stars and I thought, hey, why don't I try to be an astronomer? And so I went ahead and tried, and I took classes, and amazingly, I was successful in being able to do it. So that's basically how I became interested in space and astronomy. When you begin working in a field is an extremely fuzzy line to define. Was it when I first began reading about astronomy as a young boy, or was it when I started reading astronomy textbooks on my own in high school, or was it when I started taking classes in university, or was it when I started graduate school? Anyway, I don't mean to be evasive about this, but let's just say, for the point of conversation, that I've been working in the field since I graduated and got my doctorate in astronomy, which I got from the University of Texas in 1997. So that would put me as being in the field now for, I guess, 24 years at this time. And over that time, we have seen tremendous changes in the field of astronomy. It's actually quite remarkable, the changes that happen year to year in the field. The field has really blossomed over the last 30 or 40 years, thanks to the rise of incredible telescopes that have been able to peer further out into the universe, and in ways that we've never been able to do so before. Access to wavelengths of light that we weren't able to perceive before because they have been blocked by the atmosphere, just as an example. I could go on and on about all of the amazing changes, but I will say that for my own particular field of study, which is the origins of stars, there has been, again, tremendous amounts of advances made in that one subject in astronomy. And it's largely been because of the access to newer and more sensitive facilities that allow us to access these wavelengths that we just can't see with our own eyes. Stars form very, in a very cloaked manner. They form deep within the dark molecular clouds that pervade the galaxy. And they're dark because they're very dusty, and this dust absorbs the light from the young stars. But when you go to longer wavelengths, that dust is more transparent and it allows you to peer deeper into the cloud and see the young stars themselves forming. And in fact, if you even go to longer wavelengths, you get to actually see the faint emission from the dust grains themselves, as well as tracers of the gas in those clouds. So over these 3 decades, we've seen a tremendous growth in our ability to track that process and see it in unprecedented detail. High points would be, for example, the launch of the NASA's Spitzer Space Telescope, which was an infrared telescope that was able to take, for the first time, very complete censuses of the numbers of young stars that were in molecular clouds within our galaxy. Another high point was the launch of the Herschel Space Observatory by the European Space Agency. This was a sort of a far infrared telescope that, again, allowed the dust in those clouds to trace the structure of those clouds and allowed us to see for the first time the great environment which shapes and causes these pockets in those clouds to condense, collapse, and form new generations of stars. And then more recently, we've had the rise of a facility in South America called the Atacama Large Millimeter Submillimeter Array. And this is a collection of 66 radio telescopes that are combined into a single facility that, when all of the telescopes are pointed in the same direction, you can take the signals recorded by each and synthesize an image as if it were a telescope as wide as the individual antennas themselves. And so that very large facility has given us unprecedented sensitivity and the ability to look and actually see the environments in which planets are forming around young stars. And just last week, we had this incredible image that showed not only a disk of material around a young star, but also a disk of material surrounding a protoplanet that was orbiting that star. So that was an incredible image to see for the very first time. So we've seen these incredible advances that have really helped us understand the process by which stars form. There's still lots of questions we have. That's the way science works. Making new advances sort of opens up new unknowns that we try to understand. But it has been an incredible ride over the my last 3 decades of working as an astronomer. And I look forward to riding that crazy train for another couple of decades still. One of the things that I'm currently working a lot on lately for my scientific research is, again, to study the origins of stars. And what we see in the galaxy are these vast clouds of molecular gas. These are the cold environments in our galaxy, which are only about 10 degrees above absolute zero in the coldness of space. And in those dense environments, you have the conditions which really favor the development of small pockets that become overdense and are unable to support themselves against their own gravity by their internal pressure. And when that happens, that pocket of gas collapses to form something we call a protostar. So that's a very simple explanation about how stars form, But the details, of course, are very important because we don't understand, for example, why is it that we have a particular type or distribution of stars of different mass? The sun has a particular mass, but we know that there are stars that are about 1/10 of its mass and stars that are over 100 times its mass. Well, maybe just 100 times its mass. But in that range, we see, for example, a distribution where we have more stars of lower mass than we do of higher mass. And why is that? Why does it have to be that way? We don't really know. I mean, we have some pretty good ideas, and one of the things I've been working on is trying to understand that a little bit better. We feel it has to do with how these turbulent motions in the cloud move material around and cause them to create structures that then favor this collapse. But another thing we would like to know is, why are there stars that are multiple stars? The sun is only a single star, but most stars in the galaxy are actually in pairs or triples or more. Why is that the way it is? Is there something that promotes that kind of star formation, or is it and why didn't it happen for the sun? Why do stars form also in groups as opposed to just isolated objects? So there are lots of questions about the formation and origins of stars that we don't understand. And one thing that I'm personally doing is that I'm mapping the densest regions of these molecular clouds, the ones that are producing the most stars in our solar neighborhood. And I'm doing that because I'm trying to understand the conditions by which the gas itself is condensing into stars. Can we see, for example, the motions of this gas as it collects into these star-forming structures? Can we see how can we understand the dynamics of that gas by just using the emission of a particular molecule to trace that dense gas? And so we actually do use molecular spectroscopy ourselves to understand how it is that stars themselves form. And I'm using actually data, I'm using data from a telescope called the Green Bank Observatory, which is the world's largest fully steerable telescope. This telescope is located in West Virginia, and it was completed about 20 years ago, and it is 100 meters in diameter. And in this telescope, you can actually move it to any point on the sky. And with that, we can actually receive the faint glow from this particular molecule at a specific frequency of light, and then use its, by mapping that emission across the sky, we can then see where are the densest regions in these molecular clouds. And then by comparing to other observations of, say, the stars, we can make the connection to how much dense gas there is to how many stars are being produced. So my group here in Victoria is working a lot on that. So spectroscopy is the way of measuring the variations of intensity of light with wavelength. So the long answer, though, is that when we look at light with our eyes, we're actually seeing a spectrum of different wavelengths of light. And it's actually a relatively narrow range. Even though we see a variety of colors all the way from red to violet, that's a very, very narrow range of the wavelengths of light which can exist in the universe. And so there is a vast electromagnetic spectrum of light, which we also can use to look at the universe. But in particular, what we try to do with spectroscopy is understand how matter interacts with that light and leaves its footprints on this spectrum. So anything, for example, that has any kind of temperature emits a very broad continuum of emission at a very wide range of wavelengths. Everything does this. You, me, the sun, the stars, all of this have this very wide emission that's related to how warm we are. okay? So most of our emission, though, is actually, unlike the sun, where a lot of the emission occurs in the wavelengths that we can see, most of our emission, because we are colder, occurs at longer wavelengths. These longer wavelengths are infrared and longer. And if you were to see us with an infrared camera, you would actually see that glow, okay? So against that background of specific, of this broad range of wavelengths that everything produces, there can be actually interactions between the light that passes through a medium and the medium itself, causing that medium to either absorb that light or emit its own light. And by breaking up the light into its component wavelengths, you can actually measure how the different brightnesses at those wavelengths that can be caused as a result of that interaction between light and matter. Now, the reason that that happens is because different elements in the universe have different structures in their atoms. I mean, all atoms have the same overall structure. There's a nucleus made up of protons and neutrons, and then there's clouds of electrons around them, depending, with a number of which depends on the numbers of protons in the nucleus. Okay, so because each element has a different number of protons and a different number and the same number of electrons, because of quantum mechanics, things that I can't get into, the structure of how the electrons are around the atom changes. They actually have different types of shells, as if you will. So the heavier the atom, the more electrons, and the different electron configurations around the atom. Now, the essence of quantum mechanics is that when you get down into the extremely microscopic scale of atoms and so forth, things actually don't work on a very continuous way at all. Instead, things move quantumly in discrete differences in energy. So, for example, if an atom is excited, an electron will go from one of its lower states to a specific higher state that's defined by quantum mechanics, okay? So, for example, when a light would pass through a cloud of that element, some of that light might excite an electron to its higher state and be absorbed. And then maybe that atom will de-excite and then emit that light in another direction. But if you were to look at the passage if you were to look at that light and split it up into its wavelengths, you would actually see the footprint, the fingerprint, if you will, of that element in the spectrum, because you would see that deficit, if it were absorbed, at a specific wavelength that equaled the energy difference between those states. Okay, so spectroscopy is a very powerful technique because you are actually looking at the influence of atomic structure on light. Okay, and by that process, you're actually getting a glimpse into the atomic structure itself, because those wavelengths, those discrete energy levels, and the wavelengths that define the energies between them are themselves defined by that atomic structure. So by measuring those wavelengths of the light at those specific wavelengths, you actually get insight into the structure of the atom. Okay, so spectroscopy is, again, the way of measuring this. And you can do this with atoms, of course, but atoms are not the only things we see matter be. And we can actually have collections of atoms that we call molecules. Molecules are basically collections of atoms that have bonds between them. And by bonds, I mean neighboring atoms can actually share their electrons in a way that keeps the atoms close by. And so famous molecules, for example, our oxygen, which we breathe. You know, those are two oxygen atoms that are in that are called a diatomic molecule because they're two atoms, and they share a bond between them. Another famous molecule is water, which is oxygen with two hydrogens, one on each side, and the hydrogens are bonded to the oxygen by sharing these electrons. Now, if you were able to pass light through some cloud of oxygen or water vapor, if you will, you would actually see changes at specific wavelengths related to how that light can change the state of those atoms or molecules, and as a result trace exactly what energies are between those two states, which then again is related to how the atom is structured or even how the molecule is structured. So that's what spectroscopy, in particular laboratory spectroscopy, is, because in the 20th century, with the development of these new techniques, they were able to make these apparatuses that allowed the scientists to fill chambers with gas and then have light pass through that material, and then they could record by splitting the light up into its component wavelengths, or colors, if you will. They could then actually see the imprint or the fingerprints of those elements. And so that is essentially what Herzberg worked on, is that he was trying to understand the structure of atoms and molecules by looking at by using spectroscopy to measure the wavelengths at which certain elements or molecules would imprint on the spectrum. So most of astronomy occurs basically from the vantage point of the Earth, either telescopes from the ground or orbiting the Earth. And so we are actually peering out into the universe, a universe that is so huge we cannot travel to visit and sample ourselves. So we are left with whatever means we can to perceive and understand the universe as best we can. And the primary way in which astronomy has been able to do that is through light. So stars emit light, the sun emits light, the planets reflect light, and all sorts of, when we look at the galaxies, we're looking at the sum total of all of the light from its stars, and so forth. So there's no way we're going to be able to travel to a galaxy. They're just too far away, and it would take millions of years to travel that way at the fastest speeds. So we're left to using this messenger of light as a way of trying to understand the universe, okay? So spectroscopy has been an extremely powerful technique in actually enabling us to understand the universe. And in fact, it was the rise of spectroscopy in the late 19th century that changed the subject of astronomy into astrophysics. Because before, astronomy was basically trying to look at what was in the universe, and astrophysics is more of trying to understand how the universe works. And this tool of spectroscopy, because of its ability to trace the elements of atoms and the molecules that exist in the universe, and the subtleties in which that matter affects the light, enables us to probe the conditions of what's going on in the universe in a very interesting way. And people have been extremely clever in using the subtleties that we see in these slight differences in intensities with wavelength to be able to understand a tremendous amount about the universe. It's actually kind of amazing when you think about it, how this, because we simply can't go to these places, we are left trying to decode the information that's within light by splitting it up into its component wavelengths, and then trying to understand those slight differences in brightness with wavelength because of the influence of molecules and atoms on that spectrum. Primarily, we have seen in astronomy splitting up the light that we see with our own eyes, visible light. Okay, and so a lot of the telescopes in the early 20th century had instruments called spectrographs that would take the light from a telescope and split it up into its component colors. And then using photographic plates, they would then record those differences in brightness. But as I had said before, light exists on a much wider continuum of wavelengths than what we can see with our eyes. And we actually can use different techniques to split up the light at those wavelengths as well, and be able to record the differences in brightness at those wavelengths. And through that, we have a much broader range of being able to probe the universe because different wavelengths trace better different parts of the universe. So I would just like to tie that into spectroscopy in particular. So how does the work that I do relate to the spectroscopy of stars, planets, and comets and so forth, and what is the goal? Well, again, what I do is mostly work in what would be called the radio astronomy area. And at those, it's the same thing, it's just a different form of light. And so we break up the light into different wavelengths, and again, look using a special type of spectrograph at the differences in the brightness at those wavelengths. And because these are radio wavelengths, we're actually able to use tools that enable us to see things see the wavelengths at extremely fine details that, because of the wavelengths, are much longer than the wavelengths that we have at visible light. So we use these techniques, and so we can actually use, by breaking up the light that we get from these molecular clouds, we can actually see the different molecules, the light from these different molecules, through the emission as a result of changing their states in the very cold environments of these clouds. So spectroscopy is really important because it tells us, for example, at the very fundamental level, what kind of molecules exist in this cloud, okay? And then by looking at the profiles of these different features, profiles meaning how the brightness changes with wavelength, we can actually use that information to determine how much of that molecule exists in the cloud. And the width of that line, or that feature, as we call it, can tell us something about the motions of the gas. Because as we know from Einstein's theory of special relativity, things that are moving towards us will emit light that is slightly blue shifted, that becomes slightly bluer in color. And things that are moving away from us are actually, if they emit light, that light is a bit redder than it ordinarily would be. So because these fingerprints that are caused by the discrete energy levels in atoms and molecules, we can exist. The fact that we see a range of brightnesses across some group of wavelengths, okay, means that we can actually measure the velocities of that gas in the directions moving towards us and away from us by how much of that light has been shifted blue or red, or to shorter or longer wavelengths. And so when we observe these molecular clouds and we see the emission from certain molecules, we can then go ahead and try to understand exactly how that cloud is able to, what the motions are in that cloud, which gives us an incredibly powerful technique to understanding the environments in which stars are forming. And that I think is the key mechanism by which we use spectroscopy in the field of star formation. There are other applications as well. And one of the most important things, I think, and again, I'm sorry if I'm becoming long-winded here, is that molecules exist with other molecules in these clouds. And how much of one molecule versus another can really depend on the conditions within that cloud. For example, its temperature or its density, okay? So what we actually are able to probe with spectroscopy is how these molecules are changing into other molecules as a result of chemical reactions that occur over tremendous amounts of time and produce these molecules that can be actually quite complex. The simplest molecules have 2 atoms, and then there's 3 atoms and so forth. But we are finding ever more complicated molecules that are, again, becoming more and more like the kinds of molecules that we actually use as a part of our life. Molecules that are components that could eventually become themselves. We haven't detected it yet, but actual biological molecules. Okay, and so this gives us insight into the origins of life, because one possibility is that the seeds from which life arose on our planet may have arrived here through chemical processes in the environment out of which the Earth and the Sun formed 4.5 to 5 billion years ago. So we're actually seeing this process occur around forming stars now by using spectroscopy to probe how molecules are changing into other molecules, becoming more complicated in these environments. So it's an extremely powerful tool. The question asks, once you have found a particular molecule or atom in the spectrum of a star, what does it say and what does it mean? So my research has been understanding the gas that surrounds young stars, and not so much the young stars themselves. Those are still incredibly shrouded in material, making it very difficult to probe their own components. But spectroscopy is used quite thoroughly to explore the environments of stars themselves. And what is done is to take that light and split it up into its component wavelengths. And we usually do this at visible wavelengths. And from that, you can actually see, say, the dips of that are produced by different elements in the outer layers of a star when those elements absorb the light from the star itself and emit it elsewhere. So you see these dips, these are what we call absorption dips. And those can actually be very powerful for understanding the star themselves, okay? And just to give you a counterexample or at least another example of what spectroscopy can do, is that by measuring, fundamentally by seeing the footprint of different elements, the fingerprints of different elements within the spectrum of a star, you get to see what kinds of elements are in that star, okay? And that can actually have very important ramifications as understanding when did that star form, in what environment did that star form. And just to give you a particular example, stars have been forming in our universe for 13 billion years, and the oldest stars probably should have the least amount of what we call metals, that is, elements that are heavier than helium. Because most of the universe, when it was created, consisted of hydrogen and helium, and all of those other elements have been produced in the interiors, the cores of stars, as a result of nuclear fusion reactions and supernova, and other cataclysmic events like merging neutron stars and so forth. But the point is that those old stars shouldn't necessarily have a lot of metals within them, because there weren't a lot of metals when they formed, right? They've only produced them themselves. So by looking at the spectrum from the star, you can see by the absence of certain elemental fingerprints from the spectra that star does not have the kind of metals that we look for or that we see in the modern universe. So that can tell us something very interesting about stars itself. But the spectrum and what we see in stars can also be used to measure the temperature of those stars by the presence or absence of certain common elements like hydrogen and helium, which get excited at different temperatures that stars are at. And also the width of those lines that are seen, those features, that absorption dips that we see in stellar spectra can be used to understand the size of the star, because they can be broadened as a result of pressure, and that pressure then has an implication on how fluffy that star is, okay? And then that fluffiness comes from its size. So we can use stellar spectroscopy to get a lot of information about what a star is and how big it is and how much massive it is and how much light it is producing. And from that, we can even understand, for example, where it exists in its lifetime, because stars have follow a very prescribed track in their evolution based on how their core is doing and being able to generate further energy as a result of nuclear fusion of hydrogen in its core. And the stellar spectroscopy allows us to put on a graph where a particular star is in its temperature and its brightness, its luminosity, and those quantities are related to its current state. So the telescopes that we use are fundamentally light gathering devices, and the bigger the telescope, the more light we're able to gather, and the fainter the objects we're able to see. And so how telescopes work is that they largely take light from a large area and bring it into a focus. And so they use mirrors or reflectors to take that light from a large area, and using a particular shape known as a parabola, those light rays can come in and then reflect perhaps to another mirror, which then causes them to come to a point, okay? And once they come to a point, we can put instruments at that focal point. For example, a camera, which will take a nice picture of where the telescope is pointed. Or we can put something called a spectrograph at that location, which will take the light and it will split it up into its component wavelengths. And so we can see those variations of the brightness of colors over wavelength, and then use that information about how the environment of the matter from which the light passed through to then surmise the conditions of which that light arose. And so that's how spectroscopy functions as an effective tool, by splitting up the light, looking at those variations of brightness with wavelength, and then telling us something about where how that light either passed through or originated. So how these are recorded are actually done these days with electronic cameras, okay? So when we split up, we have CCDs all over the place. These are called charge-coupled devices, and that's a fancy way of saying calling the chips that we have in our phones, for example, right? These are electronic devices, and they're much better at capturing light than photographic film or plates, which were used back in the early 20th century to capture the light. But that material, those photographic plates and film, are not very efficient. They don't capture a lot of the light. These chips are much better at capturing light. And so when we put them in a telescope or by a telescope, they're much better at capturing the light, and allows us again to see fainter and fainter objects. And don't forget, it's important that when you split the light up into its component wavelengths, you're basically diluting that light into its different wavelengths. And so as a result, the brightness of each at each wavelength is much less than it would be for all of the light combined, right? It's like spreading something of finite amount to a wide area, you get less at each point. So by having larger and larger telescopes, you can collect more light and more efficient, and being able to spread out the light in a way that will allow you to see things better. So it's very important to have big telescopes for spectroscopy. Okay, since we have these new devices, these new electronic cameras, we can actually record the spectrum on these cameras themselves. So when we split up the light into its component wavelengths, that can fall onto a camera itself, and it can be electronically recorded as well. Okay, so that is a huge improvement, because we can then read that image as a file, and then we can then use computers to manipulate and analyze that much more easily than we could with a photographic plate. In the old days, what they had to do was take a photographic plate and then try to measure things on that plate as best they could, and it was extremely difficult because, well, the medium was very rough. I mean, but these new chips are far superior in their ability to capture light in a consistent manner, and allowing those recordings, those measurements, to be exported in ways that computers can then be used to analyze is a tremendous advance in our field at modern times. So we use computers a lot, but there's another answer to this, and that is that we can also use computers to predict what the light we see will be, so what the spectrum will look like. So we can say use what we know about physics and chemistry, and then from those laws we can then say, okay, what is the expectation that we will see of light from this environment? And then we can compare those predictions to what we observe, and from that we're able to very powerfully understand what's going on in these remote environments. So computers are used both ways, to analyze the data as well as simulate what the data will look like, and in between we get that understanding of the conditions in the universe. How does the work of Herzberg affect my work today? Well, Herzberg did a lot of really interesting work on understanding a particular molecule known as trihydrogen. Instead of molecular hydrogen, which is two hydrogens that have a chemical bond, trihydrogen is a weird arrangement of three hydrogen atoms in an equilateral triangle. So trihydrogen is interesting because there actually can be a form of hydrogen, trihydrogen, called, instead of H3, it's H2D, where one of the hydrogens has been substituted with a hydrogen-like atom called a deuterium, which is effectively just a hydrogen atom with an extra neutron in the nucleus. Okay, so H2D, well, plus, it's an ion, is a very important molecule for understanding the formation of stars. And that's because in the vast clouds of molecular gas in which stars form, the colder and denser that gas gets, a lot of the molecules that exist within that cloud become stuck to the surfaces of dust grains that are mixed with the gas. So very common molecules in these clouds, like carbon monoxide, for example, or water, they freeze onto the surfaces of these grains when they encounter them. So the colder and denser that environment gets, which is essentially the same environment out of which a star is formed, becomes very difficult to probe, because these tracers that we would use through spectroscopy are suddenly absent. They are no longer available for us to peer into that environment, because they're no longer in a state which allows us to use spectroscopy to see them. Now, this deuterated trihydrogen that I just described, the H2D+, doesn't absorb onto the dust grains. In fact, in that cold environment, because these other molecules are not around to gobble them up, they actually increase in their abundance by several orders of magnitude. So this H2D plus line becomes an excellent probe of the conditions immediately preceding the formation of a star. And so we can use those lines, those spectroscopic features from that molecule to trace the environment of those clouds. And that, I think, has a very strong connection to the work that Herzberg did in understanding trihydrogen and its deuterated forms of molecular hydrogen in his career many years ago. Because as a result of his work, we were able to understand those molecules better, and then we were able to predict where that H2D plus line exists, and from that we were able to use it as an effective tool to probe that specific environment in forming stars.